I posted some new problems for you to look at, so we can go over them on Saturday. I think maybe this Saturday we'll be able to go over some of those problems. I will send you email about that so you get more information if you wish to join live. But regardless of when we discuss those problems, you should at least look at the problems and try to work through all of them and make sure that you understand that you can do them. The problems are, of course, located on Blackboard. The topic for today is, today we review, so you should be familiar with this from calculus. Today we review vectors in Euclidean space. That's what we're going to talk about. And almost everything we're going to say today will be a review of something that you've already seen in your calculus courses. But it makes sense to at least remind ourselves all of these concepts again, because we will be using them. So most of the stuff we're going to say today is stuff you are already familiar with. So first I want to start with what we mean by Euclidean space. So let's talk about this first. So let's introduce some notation. So we use this notation. Perhaps some of you have seen this notation before. So this is, you can think of this as a bold R. And this is by definition, so this is by definition. This is the set of all real numbers. That's what the R stands for. This bold R, it stands for the set of real numbers. The reason why you make it bold is because you want it to stand out. Like you really want to have a more distinct kind of symbol for it. So you use a bold letter so that it stands out. So this is the set of all real numbers. And real numbers, as we know, it includes both rational numbers and irrational numbers. That's what we call the set of real numbers. And then related to this is something which we denote as R raised to some power, which I'm going to write n. This is some integer power. And this by definition, this is going to be the set of all so maybe I should write this as the set of all coordinates. So it's the set of all coordinates where each xi is a real number. Okay, so R by itself, this is just the set of real numbers, and R raised to the n, it's like an n-fold. It's like n real numbers together, right? It's just a, you can say that this is, you can call this an n-tuple. This is sometimes called an n-tuple. This entire thing. That's called an n-tuple.
Do you mind giving like an example?
And the coordinates that make up this n-tuple, they are real numbers. So let's just also mention some let's mention how you can visualize these. So these can be visualized for n is equal to 1, 2, and 3. So if n is equal to 1, so R1, well, I mean, this is just a set of real numbers because you only have one real number. This is just the real numbers. And these can be visualized. These can be visualized as a straight line. Okay, so the way you would visualize this is you have a straight line, and on the straight line you have the origin, right? That's kind of like the center of the straight line. And then on the straight line you have numbers, right? You have a half somewhere. You have a minus square root of 2, and you have everything else. So this entire line is denoted by R1. By R1, or you can just say R. I mean, there's no need to put a 1 over here. This is just R. This is just a set of real numbers. That's how you visualize the real numbers. You call this the real line. Call this the real line. So this is what happens when the exponent is equal to 1. Now let's see what happens when the exponent is equal to 2. So when the exponent is equal to 2, so R2, you would just say that this is the set of all pairs of real numbers. In other words, when we say a pair, we just mean a pair of two numbers together, maybe call the numbers x1 and x2. It's just a set of all pairs. And this can be visualized, and all these pairs can be visualized as living inside a plane. So this time you have a plane. So the picture here would be is instead of a line, you have a plane. And the idea is that each of these two axes represents either the first or second coordinate. So if you have, for instance, if you have a point over here, maybe that point is located at 1, 1, or maybe you have something over there which is located at minus square root of 2, 0, and so on. So R squared, or R2, represents all points, right? So these are like two-dimensional points. These are all of these points, but you now need two numbers to represent the point. And we call this the real, so we call this the real plane. You can just say the plane, but if you want to emphasize that you're using real numbers, so you say this is the real plane. And then, of course, when n is equal to 3, you're talking about 3 dimensions now. So R3, this would be the set of all triples of real numbers. So the way these are going to look like, you're just going to have a coordinate that is made out of 3 numbers. And this is, of course, visualized, and all these triples can be visualized as living inside, space. So we have actual space, and the picture that goes along with this is that you now have one of them is going towards you. It goes back into the background. So now you have something that looks like this. And if you have a triple of real numbers, then you can imagine that this triple of numbers is located, as you know, somewhere in this space. I mean, it might not be very clear exactly where that is. Maybe this will make it look a little bit nicer, just to add some detail so you get to see where it is. So here you have some point living inside this three-dimensional space, but mathematically, there's nothing preventing you from looking at Rn. You can really consider this n to be any exponent. Of course, when you go beyond 3, you cannot really visualize what you're doing anymore, but mathematically you can still do operations in that larger space. And I should also say that, as I indicated, this is called Euclidean space. So so whenever you see someone say Euclidean space, they're referring to this. The reason why it's called Euclidean space is because it's named after a Greek mathematician called Euclid. Euclid is responsible for a lot of very classical geometry, and in honor of Euclid, this is called Euclidean space. Now, when Euclid lived back in Greece, they did not have these concepts back then, but it's named in honor of Euclid because these spaces for different dimensions, they can be visualized geometrically. There's this nice geometric way of visualizing all of these spaces, and since geometry is synonymous often with Euclid, like whenever you hear the word geometry, one typically thinks of Euclid. It is in his honor that we just call it Euclidean space. So this is what we call Euclidean space. So this is what I wanted to begin with. Now, the next thing that I wanted to mention is the distinction between a point and a vector. So let me clear this screen over here. Anyone still needs this before I take this down?
Can you scroll down just to the R3? Thank you.
So the next thing that I wanted to discuss here is this distinction between a point and a vector. So if X, so what I'm going to do here is I'm going to use a bold X. If you look at the textbook, they probably do something like this. They have like this very bold X, but it's hard to write on the screen. So the way I'm going to write a bold letter is I'm just going to put an extra line through it. So this is supposed to be an X. So if X is, now here's some notation that maybe you've seen before, you've probably seen before. This means element of, this means element of. You can also say belongs to. Belongs to. So if X is an element of Rn, so we said that this is Euclidean space, then it means that X, it's a coordinate of n numbers. It means that X, that this bold X, it's just a coordinate consisting of n real numbers. Right? There's n real numbers that make up bold X. We just use a shorthand notation because writing all of this is sometimes tedious. So it's more convenient to just write a single letter X, you make it bold to just reinforce the fact that it's an entire coordinate of numbers. So if X belongs to, so if X is something in this space, then one often visualizes X either as a point or as a vector. Well, let's talk about the distinction between a point and a vector, because sometimes people get confused by this. And let's start with this. I think this is very helpful. So what we need to understand is that, strictly speaking, there is no distinction between a point or a vector. But sometimes, depending on the situation, it might be more helpful to visualize bold X. To visualize bold X as a point in space, or to visualize it as a vector in space. And a vector means it's just an arrow. Right? That's what a vector is. It's just an arrow. And it always depends on the situation. In some problems, it's more helpful to visualize this entire thing as a point, as just like a single location in space. And sometimes it's more helpful to think of it as an arrow. And we'll see instances of where it's more convenient to think of it either as a point or as a vector. So whenever you see someone say point, then they are indicating that for the current situation, it is helpful to think of points. And when someone says vector, then you should visualize X as an arrow. So for instance, to just indicate what I'm saying here more specifically, so suppose we are in two-dimensional space. Okay? We are in two-dimensional space, and two-dimensional space, this is R2. And let's suppose the vector here, well, the vector or the point has coordinates 2, 5, okay? And just to continue with the notation that we were saying, this is clearly an element of, right? That's just one example of something that is inside R2. R2 consists of all such pairs. That's just an example of one such pair that is in there. If we want to think of X, we can visualize X as a point in the plane, in which case the picture will look like this. And then the picture will look as follows. You would just draw your axes. You would draw your axes, and then you would go 2 units across, 5 units up, and then that will represent, so that would represent your X. So you can think of X like that. So if you want to visualize it as a point in the plane. But you can also visualize it, as a vector in the plane, in which case the picture will look as follows. So then the picture will look a little bit different. So then the picture would look like you would again draw your axes over here, and then instead of making a point, you would instead draw an arrow. You would instead draw an arrow going up to it. So then you would just have an arrow at 2, 5, whereas here you just have a single point at 2, 5. So it's just a difference. This is just a difference in visualization. This is called point, and this is what you call vector. And what we need to understand is that, again, strictly speaking, on a formal mathematical level, points and vectors are the same thing. In other words, they are just coordinates of real numbers and nothing more, right? They're just coordinates of real numbers and nothing more. But it is helpful to allow different visualizations. And that's why we use different words. That's why we distinguish between a point and a vector depending how we want to think about it. And as I indicated, we will see instances, we'll see a few instances this class, but we'll also see instances in future lectures where we want to allow this freedom to easily jump between thinking about this coordinate either as a point or as a vector, depending on what kind of problem that we're doing. So what I wanted to do after this is to go over some vector operations. So let's review some vector operations that you should be familiar with. Now, let me just wait a little bit to make sure that people have everything they need on the screen before I clear it. Anyone still need this?
I think we're all good, Professor.
Okay, so let me just clear the screen. So here are some vector slash point. Okay, I'm putting these together because, as we just said, mathematically it's the same concept. It's just a coordinate of numbers. So here are some vector point operations that we often use in linear algebra. So we've seen these before in calculus. So you've seen all of these operations before in calculus, and we're just going to review what these are. So let's start with, so the first operation, vector operation that I wanted to mention, so this is the first one that we should mention is so this one is called multiplying a vector by a real number. Or sometimes you say multiplying a vector by a scalar. The word scalar, when you see the word scalar, it is just another way of saying real number. I mean, they're synonymous. And what this operation says is that if you have a vector, I'll just say a vector, or you can say a point, but if you have a vector, x, and what is a vector? A vector is just a collection of n real numbers. So it's a coordinate consisting of n real numbers. And if you have a vector, and you can always emphasize, it's not necessary, but you can emphasize that this is an element of, so it lives inside this space, this n-dimensional Euclidean space. So you can say it's an element of r to the n. So if you have a vector and you have a real number, which is what we call a scalar, and let's suppose we call the real number a, and a is just a real number, and the way you emphasize this symbolically is you would say that a belongs to just the set of ordinary real numbers. So this is just a real number, so you just write r. So the common notation in linear algebra is if you're using a lowercase letter, an ordinary lowercase letter, that should indicate to you that you're talking about just a real number. When you have a lowercase letter that is bolded, so if you look at the textbook and they make it like thicker, then that should indicate to you that you're talking about like an entire vector in some larger dimensional space. So if you have a vector and you have a scalar, you can multiply them together. So you can do a multiplied by x. And the way you do that, that's equal to, and this is by definition, this is how you define this product. So by definition, this is equal to, you simply multiply all of the coordinates by a. So you just have ax1, ax2, right? You basically distribute the a on each coordinate. So that's the way you would visualize it. So for example, if you have x, that is the vector 2, 0, negative 1, then if you multiply it by, let's suppose, 3, then 3x would just be the vector 6, 0, negative 3. Okay, that's all what that's saying. You distribute this 3 on each piece, right? You just distribute it in on each piece. And there's a nice way of visualizing this. So there's a nice way to visualize this operation. There's a nice way to visualize this scalar vector, the scalar vector product. The scalar vector. And you probably recall seeing this picture in a calculus class, but the way you think about it is, if we think of x as a vector, so if we think of x as a vector, then the scalar vector product simply expands the vector by a multiple of a in the direction of the vector. So for instance, if your vector looks something like this, if this is how x looks like, then 3x, so if this is x, then 3x, maybe I should use a different color over here, then 3x is going to look like this. It's just going to be 3 times as long. This is going to be 3x. So it just expands it by a factor of 3. So this is just 3 times as long as it currently is. Now there are some small subtleties here. For example, if the number that you're multiplying it by is a negative number, then it goes in the opposite direction, as we know. But if the number is positive, it just gets expanded by that factor. And there's also another small subtlety here, is that if the number you're multiplying it by is smaller than 1, like for example, if you multiply it by 1/2, then you're just going to cut it. You're just going to cut it in half. So that's what happens here. So this is the. Maybe I should also make this comment: if a is equal to 0, then if you do this product, so if you multiply a vector by 0, so here we talk about multiplying a vector by a real number. So we're saying, well, what would happen if you multiply it by the 0 number? Well, then all of these coordinates will now be equal to 0. And so you would end up with a coordinate consisting of 0 numbers. And this has a name to it. This is called the 0 vector. This is what we call the 0 vector. You can think of it as representing the origin. Right? That's how you can think of it. You can just think of it as representing the origin. And usually it is a good idea to distinguish the number 0 and the vector 0 by making 0 bold. So it's basically the difference between writing 0 as a number versus maybe writing something like that, 0 as a vector. I mean, you could just write, I know some people put like a arrow on top. You can write it like this. I just think that this is a little bit more aesthetically pleasing rather than doing something like that. I mean, it's up to you how you want to write it, but it's a good idea that you distinguish them somehow, because sometimes people make a mistake. Because if you're solving a problem that involves the 0 vector, then you really need to understand that you're supposed to have an entire coordinate of zeros all the way across. And if you're being a little bit sloppy and you just write a 0, you might accidentally throw off your calculations and mess something up if you're not being that careful. I mean, if you somehow mentally understand that when you write a 0, you mean the 0 vector, then I guess that's fine. But it's just as a way of being careful, you sometimes want to distinguish between these two. Okay, so this is our first operation. This is called the scalar vector product. The next one that we're going to discuss, so I'll scroll it down here. The next one that I wanted to discuss is the sum of two vectors. This next operation that we're going to look at, this operation is called the next operation on vectors is called vector sum. Or you can say it is a sum of two vectors. So how does this one work? Well, let's just quickly recall. I know that you've seen this in a calculus class, but again, it's a good idea to review this. So suppose x is a vector. So that means it consists of a coordinate of n numbers. So this is xn. And y, and that's another vector. It consists of a coordinate of also n numbers. So you can write as a shorthand. You can also write, it's not necessary, but I'm just doing it to teach you notation. You can also write, you can say that x, the vector x and y, they belong to this space Rn. That's the way you write it. That's like a shorthand way of writing it. If I just write that x comma y belong to Rn, that is immediately telling you what this notation tells you. It immediately tells you that x and y are coordinates consisting of n numbers. So that means x looks like this and y looks like this. So you have two vectors. Then we define the vector sum as follows. So this is how you add two vectors together. So we define the vector sum. So if we do x Let me try that again. Let me make it look a little bit nicer. So you do x plus y, and that is equal to, and this is again by definition, we are defining what it means to add two vectors together. And by definition, that operation is what you think it means. It means you just add component by component. So you add the first two components together, you add the next two components together, and you do that all the way until the last components, and then you just add the last components together. So the picture here is quite simply, if you want to look at the picture, is you're just adding these together, you're adding these together, you're adding those together. So you're adding them separately from each other. And this is what you would get. So for instance, just to make it even simpler, if x is the vector 2, 3, 0, negative 2, and y is the vector, let's suppose, 3, 2, negative 3, 0, then if you were to add them together, you do it one component at a time. You do it component by component. So you have to look at the first component here. The first component is 2. This one is 3. You add them together, that's going to give you 5. Then you have 3 and 2. That's going to give you 5, and so on. So if you do this one step at a time, then this would be equal to 5, 5, negative 3, negative 2. So that's what you have if you do the vector sum together. Yes, Eric, you have a...
Can you add vectors of different sizes, or it might be length? I don't remember if it's size or length for like the amount of elements in it.
Yeah, so when you add vectors, you make sure they have the same dimension. So you can say the length. That's fine. You can say vectors of the same length. You can also say the dimension, because these are n-dimensional vectors. So you want to make sure that the vectors have the same length, because otherwise you're not going to have room to add them. The vector sum would be undefined if they have different lengths. You have to make sure you're in the same Euclidean space. The vectors are coming from the same Euclidean space. But that's a good observation, that they need to have the same length. And there's a nice way of visualizing vector sum. So there's some nice geometry. There is a nice geometrical picture that represents the vector sum. And the picture looks like this, and you've probably seen this in a calculus course, but let me draw the picture for you again. It's a very nice picture. It says that if, so this is your, so that over there is your origin. So that is your origin. And we have an x. Let's suppose out of this origin, so out of that origin, we have some vector x, and then we have another vector. Let's suppose we have another vector. Call that y. Then the way you can visualize the vector sum is you complete the parallelogram. So these two vectors, they make up sides of a parallelogram, like that. And then the vector sum would be the diagonal of the parallelogram that you create. So that would be, this would be x plus y. Okay, so basically what we're saying is the vector sum can be visualized as the diagonal of the parallelogram, which is determined by x and y. And of course, for those of you who have a physics or engineering background, you immediately realize why this is important, because this is exactly how forces act. if the origin represents a body, and on this body you have two forces acting on this body. So like, for example, let's suppose you have two pieces of rope acting on a body, and one person is dragging the rope in this direction, and the length of the vector is indicating the magnitude of the force that you're dragging it in. And you have another person dragging this body in the other direction with a certain force magnitude. Then the vector sum is going to tell you this will be the result if the two forces are acting together. There's some kind of compromise that is taking place between x and y, and then the body is moving along this direction with that kind of magnitude. So that's what's going to happen if you add them together. So this is called vector sum. Now, the next operation that I wanted to mention, so this is operation number 3. It's called norm. This is the third. This one is called norm. So if x, let's suppose x is an Rn, then we use the notation. And this notation, there's two ways to do it. There's two different notations here. Some people write x and they put absolute values around the vector, or alternatively, some people write it a little bit differently. Some people put an x and they put 2 bars around it. So it's two lines. And this is called, so both of these are the same notation. This is a different notation for the same concept. This is called norm. This is called vector norm. Vector norm. So what is a vector norm? A vector norm is the length of a vector. So if x has coordinates x1, x2 up to xn, then the vector norm, so it depends how you want to write it. I'll write it with 2 lines. Then this is the length. This represents the length of the vector. It also represents, alternatively, it also is the distance of the point x to the origin. So you can also think of it as a point. It represents the distance to the origin. And we'll write down how you calculate it. So the way this is calculated is it's equal to, the way you find it is, it's the Pythagorean theorem. It's the sum of squares. It's the square root of the sum of squares. So it's x1 squared plus x2 squared plus xn squared. So that's what it is. It's the square root of the sum of squares. That's what we call the vector norm. So for instance, I'll do a 2-dimensional example because it's easy to draw. But if, let's suppose x is -3, 4, then the norm of x is equal to, it's the square root of -3 squared plus 4 squared, which is, this is equal to 5. And the picture that goes along with it is, if you draw your plane and then you have -3, 4 up here, and this represents your vector, then the length of that vector, so the length of that vector is equal to 5. That's what the norm measures. The norm measures the length of the vector. You can also say magnitude. That also works. You can say the magnitude of the vector. I'm not sure what kind of language they use in a calculus class. I'm used to saying norm. That's the way I'm used to saying it. But if you say magnitude, that would also be fine. An alternative. So alternatively, you can also visualize this using points instead of vectors. So you can also think of it like this. If you want to use a point visualization, picture will look a little bit different. You would have your axes, and then you have x representing the point, and then what does 5 represent? Instead of representing length, it just represents the distance. It just represents this is like the distance. This is the distance to the origin, which is at 0, 0. So that's your origin, and that's the distance. So it's like the distance that is between them, the distance to the origin. So this is the way you find the norm of a vector. You take all of the components, you take the sum of squares, and then you take the square root of that, and that gives you the distance to the origin. Now, one way this can be used is to find the distance between the 2 points. So if you have 2 points in Euclidean space, so let us call those points x and y. But we have 2 points x and y, and these are points in Euclidean space, then we can compute the distance. Then we can compute the distance between x and y by doing the calculation. Here's the way we're going to do the calculation. We would do x. From x, we subtract y, and then afterwards we take the norm. That's what we do. And by the way, that's the same thing as y minus x. It's the same thing as that, because it does not matter whether you write x minus y or y minus x, because when you do a norm calculation, you can see that the quantities are being squared. So the minus sign will go away. But here we need to specifically, here it makes more sense to visualize x and y as points and not as vectors. So earlier in today's lecture, I said that sometimes you want to think of them as points, and sometimes you want to think of them as vectors. Here's a situation where you want to think of x and y as points. If you think of them as vectors, then this quantity starts to make less sense. So if you think of x and y as points, so if this is x and this is y, then what you're doing is you are calculating the distance between x and y. That's what you do. That's determined by x minus y. If you think of x and y as vectors, then the picture is not as nice. If instead you had a vector representation of this, then you would have something that looks like this instead. That you would have your y over here, and you would have maybe your x over there. And I mean, you're not going to say the distance between the two vectors because these vectors already intersect. You see these two vectors intersect, so there's not really a distance between them. You really want to say it's the distance between their endpoints, but then you're specifically only thinking about the end. You're only thinking about the points. So in this kind of situation, when you're drawing the picture, it makes more sense to it would make more sense to have this kind of picture in mind. So this is how you find the distance between 2 points in space. Now, the next important operation that we often frequently use is called the dot product. So just to answer someone's question, x minus y and x plus y are going to give you different calculations. You can do it in a specific example and see what happens.
But they're not like the same magnitude or length or whatever?
No, they're not going to be the same magnitude. You can just come up with some random examples and see it's not going to work. So the next one that we're going to discuss, this one is called the dot product. This is called the dot product. So let's recall the dot product. It's also sometimes called the scalar product. So let's see how this would work. So the way the dot product works is, suppose x, so you have one vector, and then you have another vector, and they have the same length, you will notice. So you have two vectors of the same length here. Then the way the dot product is defined, so it's x and y, and you put like a dot between them. And this is equal to, and this is by definition, this is how the dot product is defined. By definition, what you do is you multiply component by component, but you make sure you add up the answers. So this is what you do. You make sure that you add them up. If you want to use a fancy notation, you would write it like this. You would write xi multiplied by yi, where the index I ranges from 1 to n. That's the other way you can write it, if you want to use the sum notation. So for example, just to give you a very simple example here, if let's suppose x is this vector and y is this vector, let's suppose, then if you want to take the dot product between them, this would be equal to, you have to, the way you want to think about this is you want to do it, again, component by component. You would multiply these two, you would multiply those two, you would multiply those two, and then you have to add the numbers together. So you would do 2 times 0, which is 0. Then you would do plus 3 times 2, which is 6. And then you would do -2 and 5, which is -10. And then the answer will come out to be -4. So that is the way you take the dot product. And just some alternative notation for the dot product. Sometimes people write, maybe you've seen this before, I'm not sure. It's not commonly used in a calculus course, so this might be new to you. But sometimes the way people write the dot product is they put like these 2 brackets, and then you put the 2 vectors separated by a comma, and this is just simply another alternative notation for the dot product that sometimes people write. This is just you're kind of pairing the two vectors together. The two vectors are being paired together. So one thing you have to be careful about, so be careful, the dot product is no longer a vector. It is a scalar. The dot product takes two vectors and returns back a real number. So this is why it is called a scalar product, since the end result is a scalar, right? When you actually do the dot product, you end up with a real number in the end. So if you look at this calculation that we just did, if you do x multiplied with y, you end up with -4, which is no longer a vector. And that's why we sometimes call this a scalar product. Now, what's the significance of the dot product? Anyone remember why the dot product is important? So why is the dot product important?
Does it give you the angle between two vectors?
Yes, that's what it's related to. So the dot product is important. The dot product is important because it is related to the angle between the two vectors. That's why we care about the dot product. The way mathematics works is you can define any concept you want, but you want to make sure that whatever you end up defining has some kind of significance to it. So you can, of course, define this product, but it does not really tell you why you care about it or what you ever use it for. But the reason why we discussed the dot product and why it's important to working in space is because it helps us find the angle between the two vectors. So recall that if theta is the angle between two vectors x and y, then we have the relationship that, so here's the relationship that if you do the dot product between the two vectors, it is equal to, it's not quite the, so it does involve cosine, it does involve the cosine of the angle. And then you have this, it's x, it's the norm of x, then you have multiplied by the norm of y, and then multiplied by the angle between them. So for instance, the picture here would look something like this. If that's your origin, and this is your vector x, and then you have another vector over here, maybe I should not draw it like this. Maybe I should draw it like this. You have another vector over here, y. There's an angle between them. Now, the nice thing here is you can actually measure. It's up to you how you want to measure the angle, because you could say it's a little bit ambiguous. You can either look at the acute angle, or you can look at the obtuse angle, which would be 2 pi minus theta, the other way around. But it really does not matter whether you use the acute angle or the obtuse angle, because cosine will actually be the same thing. So note, this is an identity that we have, that cosine of theta is the same thing as cosine of 2 pi minus theta. Whether you decide to measure the angle with the smaller angle, or whether you decide to measure the angle with the larger one, in the end, you're going to get the same answer, because if you use the larger one, cosine of the larger one will be cosine of the smaller one. This is just a simple trigonometric identity. And so the dot product comes out to be the same thing. And so there's this nice fact. So the special case is when the dot product is equal to 0. This means that the angle is pi over 2. In other words, the vectors are perpendicular together. So we can say that the two vectors x comma y are perpendicular to each other. That means intersect at right angles. If and only if their dot product is equal to 0. If and only if their dot product is equal to 0. So this is the nice way of determining if two vectors are perpendicular. You just have to take their dot product, and that will tell you if they are or if they are not. And finally, I wanted to finish with one last concept, and that's something about the cross product. And it's very special to only three-dimensional space. So let me finish with this. So this is our last concept that we wanted to mention for vectors. Now, usually in spatial problems, we work in R3. For those of you who are engineering students, you probably work in R3 all the time. You draw models and constructions in R3. So usually in spatial problems, we work in R3. And the more general, the more general dimensions are for non-spatial problems. If you're wondering, do we ever use R to the 50 or something? You do, but not for spatial problems. Like very often, in certain circumstances, you might have a quantity that depends on many different variables, and they're not necessarily spatial variables. It could depend on time. It could depend on pressure. It could depend on something else. And every single time you have this extra parameter that you have to keep track of, you're technically going up a dimension. So you may not be able to visualize what you're doing anymore, but at least the mathematics still continues to work. So in spatial problems, like problems that you're trying to coordinate yourself in space, you work in R3. And in three-dimensional space, there is a special vector operation that only exists in three-dimensional space, called the cross product. You only have the cross product in R3. There is no cross product for any other dimension. And you're going to see the reason for that very soon, why it's special to R3. But the way the cross product works is you have two vectors. So let's write them as x1, x2, x3. And then you have another vector, y1, y2, y3. And I'm sure you've seen this before, but the first time you see this, this looks very confusing. So this is what we call the cross product. And the cross product is equal to, by definition, and this is going to look very confusing, it's equal to this. It's x2, y3 minus x3, y2. Then it's y1, x3 minus x1, y3. and then it's x1, y2 minus x2, y1. Okay, that's what it is. It's a very complicated, not memorizable formula. You do not actually calculate it like this because this is impossible to memorize. You're not going to memorize this. The signs, everything is sort of very, but I'm going to show you a way you can calculate it. I know that in a calculus class, they show you how you can compute it using determinants, but I want to deliberately avoid using determinants for the time being because we'll discuss determinants later in the class. So the way you do it in a calculus class, you set it up in some kind of matrix, and then you use a determinant to find it. That's like the mnemonic that you use. But I do not want to talk about determinants yet because one of the intentions of the class is to get to the determinant first before we get to use it. So I'd rather not use the determinant at the moment, but I wanted to just say the significance of the cross product. The significance of the cross product is that it produces a vector that is automatically perpendicular to x and y simultaneously. So the picture here is this. So you have two vectors. So here we are in space. We have one vector x. We have another vector y. Let's do another picture over here. And the cross product, when you do the cross product, when you do this complicated formula that you do not have to memorize, I'm going to show you a way you can do it without determinants or anything like that very soon. That if you do this, you get a vector, and it's a vector that is going to be perpendicular to both x and y at the same time. This is, by the way, the reason why the cross product only exists in three-dimensional space, because in four-dimensional space, you have more than one vector that's going to work here. So it's a little bit ambiguous which one you pick. That's why it's very special to three-dimensional space. So if you look at all of the vectors, you're going to get something that looks like this, right? I mean, it has to be something that's perpendicular to x and y at the same time. This is x, this is y. So think of x as going to the right. Think of y as going towards the board. And then this is perpendicular. This is now perpendicular to x and y. So whatever the cross product is, it has to lie somewhere on this line. So it can either point up or it can point down. So how do we determine? So how does one determine the cross product? How does one determine the cross product geometrically? So the way you do it is you use something called the right-hand rule. And the way it works is you put your right hand on the first vector and you curl your fingers towards the second vector. And your thumb will point in the direction of the cross product. So for instance, in this picture, so let me draw this a little bit bigger. So here you have a vector. Here you have another vector. So let's suppose this is x. Let's say that this is y. And we want to calculate x cross y. So x, this is vector number 1, this is vector number 2. So here's how you do it. So you're going to position, this is your right hand. So I'm going to try to draw a picture of a right hand. So this is your right hand, this is your thumb, okay, this is your right hand. You put your right hand on this vector. And then you're going to curl your fingers. You're going to curl your fingers to y. And if you do that, you will notice that your thumb is pointing up. Your thumb is pointing in that direction. So that means when you take the cross product between x and y, the cross product is going to be pointing in that direction. If you do it the other way around, the picture is going to look a little bit different. If you decided to do it the other way around, if you decided to do y cross x instead, then the way this is going to look like is if you try to position your right hand in this kind, so let's suppose you try to position your hand like this, okay? This is your right hand. Now imagine trying to curl your fingers towards x. The problem is your fingers cannot reach x because x is on the other side of your fingers. So your fingers cannot reach x. So instead what you have to do is you have to position your thumb, you have to position your hand so it is pointing downwards. That would be the way to do it. You would have to position your hand like this. This would be your thumb, that would be your hand, okay? Now your right hand is, well, actually I drew that badly. I drew a left hand, right? I accidentally drew a left hand, if you noticed. So let me try doing that again. So these are your fingers, okay? And then your thumb would point down here, and that would be your right hand. Okay, so now your right hand is pointing in the right direction, because if you've imagined that your right hand is pointing down, then now your fingers are able to reach the vectors. Your fingers are able to curl, and they're able to reach x now. So now you can do it. So now you're able to reach x. Okay, so that would be the way you do it. So, so notice that one thing you have to be careful about is x cross y is the negative of y cross x. So here it's anti-commutative. If you do it in the opposite order, you get the negative answer. Now I wanted to just finish with one last thing right before we go. It's going to take a few more minutes to say, is I wanted to show you, so here's an alternative method for calculating the cross product. Yes, Eric.
The on the right side of the like notice that equation, is it like is it like y cross product x is like its own thing negated? Like, is that answer negated? Yeah, is it like that, or is it the other way?
Yeah, it's that.
Okay, just making sure.
Right, it's the negative of the answer that you would get. If you're wondering why you have to use the right-hand rule, if you're doing mathematical problems, the formula automatically will do it for you. But people who have an engineering background, when you actually have to visualize things with your own eyes, you have to have a sense of which direction the cross product is pointing in, so you take it in the correct order. So let me just show you an alternative way to do this. So recall, you have these basis vectors. So you have what you call I. This is the vector 1, 0, 0. You have something which you call j. This is the vector 0, 1, 0. And you have a vector called k, which is the vector 0, 0, 1. And you have these rules that if you take I cross I, that's going to give you the 0 vector. If you do j cross j, you're going to get the 0 vector. And if you do k cross k, you're going to get the 0 vector. And if you mix them, then this will give you k. And if you do j cross k, you would get I. And if you do I cross k, you would get j. So the relationship here is that it goes in a cycle. There's this cycle relationship. This is I, this is j, this is k, and you have this cyclic relationship. That what this is saying, if you do I cross j, you get k. If you do j cross k, you get I. If you go backwards, then you change the minus sign. So like, for example, if you do j cross I, you get negative k. And you can see this geometrically, because if you draw the coordinate axes, for instance, so here's the coordinate axes. So if you draw the 3 basis vectors, this is the vector, this is I, this over here is j, and this over here is k. And now if you use the right-hand rule, if you do I cross j, if you position your right hand, so your thumb, so your fingers point in the direction of this vector, and you curl your fingers, you will notice that your thumb is pointing in the direction of k. So I cross j will give you k. So all of these come from the right-hand rule. And once you have that, once you have this relationship, you can now calculate the cross product very easily between 2 vectors. So let's suppose x is the vector, let's just make something up, 1, 3, 0, and y is the vector negative 2, let's suppose 2, 1, let's say. Then the way you do the cross product, let's suppose you want to find the cross product. You want to find the cross product between x and y. The way you would do it is you would write x in terms of the basis vectors. So this would be I plus 3j, right? You write it in terms of the basis vectors, and you take a cross product between negative 2i plus 2j plus k. And the way you do this product is you just use the distributive law. You just distribute the cross product on each piece. So you just distribute these, and then you just distribute these. And what you have to keep in mind is that if you take the cross product with the vector and itself, it's going to give you 0. It's going to give you the 0 vector. So a vector crossed with itself will give you 0. So if you take the cross product with itself, it's going to give you 0. So like, for example, we have I cross j. So I cross I is going to give you 0, but then you have I cross j. So if we write this out, we would have I. We're not going to write I cross I because that's 0, but we will write I cross j, and you have a factor of 2, and then you have I cross k, like so. So all what happened was that you do I. So I multiplied by itself gives you the 0 vector. I multiplied by j, that's just I cross j. And I multiplied by k is just I cross k. But now you do it with the other one. So you do 3j and negative 2i. So if you multiply those together, they will give you negative 6 cross I. Then you would have plus 3j cross k. Because you see, if you do j multiplied by itself, the cross product of j with itself will give you 0. That's the 0 vector. But so you have to do 3i cross negative 2i. So it's j cross I. And on the last one, you have j cross k, j cross k. And now that you have it set it up this way, you just use these properties. So these properties tell you how to do the cross products. So now you can fill these in. I cross j can be replaced by k. This is just k. I cross k, this is negative j, because you're going backwards on that cyclic, on that circle. J cross I will give you negative k. And j cross k, this will give you I. So this is what you would get. And then when you write this out, this is 2 times k. So what is k? 0, 0, 1 plus j, which is 0, negative 1, 0. And then you have negative 6 and negative k, so that would be plus 0, 0, 6. And then plus 3 times I, which is 0, 0. And when you put everything together, what do we have? I mean, you just add them together. I mean, you add them together, and that's going to give you the answer.